Real-world biological signals are rarely the clean, repeating waves found in a physics lab. They are jagged, inconsistent, and dynamic. For the first half of the 20th century, deciphering these signals meant reading them as physical ink on a paper chart, a process limited by the speed of the pen and the eye of the observer. Digital processing changed the standard. The Fast Fourier Transform, or FFT, and the Welch method became the reliable tools for extracting frequency power from stationary signals. But while the FFT is technically perfect for long, stable datasets, it fails when applied to the specific constraints of the human body. There are two specific barriers that stop the FFT: signals where frequencies shift over time, and recording windows that are simply too short to process. Overcoming these failures requires moving past the standard transform. We have to shift our logic toward time-frequency analysis and parametric autoregressive modeling. Mastery of this field isn't about running the default code. It's about recognizing the exact mathematical boundaries of the FFT and knowing which algorithmic engine to use when you hit them. The first blind spot is temporal. A standard frequency plot can tell you exactly which frequencies exist in a signal, but it permanently deletes the information of when they happened. Consider this 10-second signal, a 10 and 20 Hz wave layered simultaneously. Now a second signal with the exact same components, but happening sequentially. If we apply an FFT, both results are mathematically identical, showing equal frequency peaks. By looking only at the frequency spectrum, there is no way to know the original order of the signal. The time vector has been completely discarded. This makes the FFT insufficient for audio or EEG data, where the sequence of frequencies is what actually carries the meaning. To fix this, we have to use a spectrogram, a compromise that trades some frequency precision to regain that lost temporal localization. Solving the when problem requires moving beyond the flat two-dimensional spectrum to track how frequencies evolve across the axis of time. The second blind spot appears when we are forced to work with extremely short data windows, sometimes as few as 64 samples. The FFT requires a long sequence of data to resolve frequencies that are close together. Without enough samples, the transform suffers from spectral leakage, where the power of one frequency bleeds into the next. Imagine a signal with two tightly packed frequencies, 10 Hz and 12 Hz, hidden inside a layer of random noise. On a short dataset, the standard Welch method produces this, a single indistinguishable blue blob. The math cannot separate the 10 Hz peak from the 12 Hz peak. This isn't a problem you can fix by changing overlapping windows or segments. It is a hard mathematical limit of the transform itself. When the data length is fixed and the frequencies are close, non-parametric methods are blind. We have to stop trying to transform the data and start modeling it. The premise of parametric modeling is different. Instead of transforming the messy raw signal, we create a mathematical model of the system that generated it. This is the autoregressive AR model. It assumes the signal has memory. The current sample, x sub n, depends on past samples. The algorithm uses a sliding window over previous samples, adding a random noise variable to predict the next sample. We aren't searching for frequencies yet. We are searching for the weights, the AR coefficients, that best define how the signal relies on its own history. The most important setting here is the model order, p, which tells the equation exactly how many past samples to consider. If p is 2, we underfit the model. The equation oversimplifies the signal, resulting in a flat curve that misses the actual frequency peaks. If p is 50, we overfit. The model memorizes random noise, creating false peaks that don't actually exist in the raw data. For most biological signals, a model order between 16 and 28 provides the necessary resolution without compromising the stability of the output. By modeling the memory of the system, we compress thousands of noisy samples into a small set of coefficients that isolate the signal's underlying frequency profile. To find those coefficients, we use the Burg method, an algorithm designed specifically for high-resolution frequency estimation. Standard methods look at forward prediction error, E sub f, measuring how well a sample predicts the one that follows it. But the Burg method is bidirectional. It simultaneously calculates the backward prediction error, E sub b, to see if the sample can accurately predict the past. By minimizing the sum of both the forward and backward errors, the algorithm creates a much more stable and accurate model of the signal. The result is clear. Where the Welch method showed a single blob, the Burg method produces two sharp, distinct peaks at exactly 10 and 12 Hz. By minimizing bidirectional error, the Burg method extracts precise frequency information that would be invisible to a standard FFT. The goal of signal processing is to choose the right tool for the specific constraints of your data. Rule 1. For long, stationary data, standard FFT methods are robust defaults. Rule 2. If your signal is dynamic, use a time-frequency spectrogram. Rule 3. For short data windows with close frequencies, use a parametric model like Burg. Treating the Welch method as a universal solution will lead to misinterpreting your most critical data. Advanced analysis is about looking past the default functions, recognizing the mathematical limits of the data, and selecting the specific engine required to decode it.